developers know this, I'm kidding. The people almost right? Almost, does everybody program JavaScript? How about people that program JavaScript? Okay. Maybe 60, 80%. How about people that program PHP? Carl? Sorry. Oh, yeah, we said that. Java? I'm really, really sorry.
We are too.
That's the spirit. So this is kind of an interesting thing. For me, one of the things that's kind of exciting for me is I go around and do these talks, and I always do this, and I ask people, JavaScript is becoming one of the most universal languages amongst developers because we all like this thing called the web. I heard it's going to take off one day. You know, maybe make some people some money. I don't know. Was anything else around for like the first .com crash? Yeah, that was really brutal. That was not a lot of fun. Hopefully we're not going to repeat that. Why not treat TechCrunch for a bit? It would just be depressing. Alright, so this one, oh, it does work. So this is me. That's me on Twitter. Feel free, thread, presentation, you know, to hold praise and adulation or just, you know, talk shit about me, it's fine. Either of those things is completely acceptable. I work for a company called Join. We are the sort of sponsors of Node. We pay several full-time developers, including myself, to work on Node and to do sort of Node-related things. I'm actually out here because we're working with a company in Malaysia to spin up our cloud technology in this region. So that's actually that's the job that I've been doing for the past couple of weeks. I also spoke at a conference for the MIMOS agency, the government agency here, doing technology innovation. So that's kind of fun too. But this cloud is being launched tomorrow, and it's going to have all of the joint software that we run in the US with our Node.js platform as a service. And that's going to be available starting tomorrow. I'm writing this book. The animal is a commentary. I actually asked them for a narwhal, and apparently they already had a book with a narwhal on it, which is a book about podcasting. And they didn't think it was a good argument that nobody gives a shit about podcasting anymore, and they should give the animal to me. Apparently that wasn't sportsmanlike of me. So instead, they gave me the commentary through, which is native to Southeast Asia. So that's good. We like him, he's cute. He's an actor, my editor told me, as I think for an animal. So the point of this talk is a language for the internet. So I think to sort of go back and to start from scratch, it's like, what is the internet? So for a lot of people, that's Google. You know, I used to work for Yahoo, I'm not better. You know, but you know, what is it doing? Well, maybe something like this. You know, where you're doing search, and you get like the Google Instant, right? This is what we're starting to think of as the experience that we expect with internet applications. That instant, you know, it's got drop down, it's got search suggestions. You know, it's not just that kind of basic search page from the 2000s. You know, it's got a lot more interactive. You know, and actually I was searching about bikes. This is my bike. She's called Eleanor. I might get stuck. She's a beauty. Yeah, she's a beauty. She's a pixie. You know. I have a cycling app, I can show you that later if you're interested in those things. What else? Facebook. So you guys use Facebook? Does anybody use Facebook? No. Yeah? No? No! You know, this is, you know, the Facebook chat experience. This is the kind of thing that we think of as the internet. This is the kind of application that we want to build. You know, when you talk to a client and people say, you know, I want to build this is the kind of standard that people expect. iPhones. Who has an iPhone? I have an iPhone. Android. People have Androids. Yeah. So smartphones. This is what we think of as the internet, right? I personally get really grumpy when I travel around a lot because, you know, 50 years ago, $60, which is what 180 ringgits, right? When I say, yeah, it's like ow, right? It's really painful because I'm so used to having the internet on my phone when I'm in the States, right? It's like I use Macs, I use like all of these things, I check my email all the time, you know? You're so used to this because this has become the internet. iPads. Does anybody have an iPad or a Samsung tablet? Yeah, there's one in the audience, right? These are becoming the internet. You know, I cook using recipes from my iPad. Right? There's like all of these things that we do, and this is rapidly becoming what we think of as the internet. Does anybody know what this is? Yeah. What is this?
It's like a GPS.
It's FedEx delivery loop, right? Yeah. So every FedEx guy, every UPS guy, every guy that delivers packages, every guy that sorts packages in a warehouse, every guy that like does all of these things has a little device. In the supermarkets in America now, the guys that stack the shelves have a little barcode scanner which is attached to their finger, and they go around scanning all of the items because they just like doing stuff all day. All of this stuff, you might not think of it as the internet. All of this stuff is built using internet technology. Like all of this connectivity, all of these wireless devices, all of these technologies are internet. This is a fun one. So this guy is in a bus shelter in San Francisco. And this is a full sort of human-sized touchscreen billboard. And it's interactive and it's a game. And basically, they set them up and they had different neighborhoods of San Francisco competing for the highest score. And they're sort of, like, is North Beach smarter than Summer, or whatever. And obviously not. Summer's full of all the startups like Click and such. And they say they employ clever people or something, I don't know. That's my clever argument. So this kind of thing, this is the internet. This is where we're pushing things. We have all of these devices, all of these things that we can build that we're connecting to the internet. The internet is no longer just a guy with a fixed desktop computer in a university connected to a bunch of other universities. The internet is like all of these things. It's all of the mobile devices. It's all of those. So what we're looking at a landscape that has more features. We have more users. I mean, especially in Asia region, South America, Africa, right? We're bringing more and more users online every day. Lord knows how many people are getting online in China. And like all of these things, having an impact. More devices. Everybody has 2, 3, 4 devices. And all of that brings more data. So I was working at Yahoo. We would aggregate the logs from Yahoo.com, which is one of the things I worked on when I was at Yahoo. Yahoo was aggregating something like 15 to 20 terabytes a day of data onto their Hadoop clusters. Their biggest Hadoop cluster is 2 petabytes. Yeah, right? Think about that. So think about like the scale of data processing. That's one company, right? Think about Google. Think about Facebook, Twitter, right? Think about IBM. Like all of these companies, the amount of data is immense. So this is the challenge. This is like the landscape that we're moving into with the internet, and it's kind of, it's difficult. So I like to sum it up with some incredibly technical graphs, which is, as you have more stuff, the cost goes up. And as you can see, I'm clearly an economist. But this is like a real problem. So this is the problem of if we keep doing things in the same way that we did before, as we like add more users, more data, more features, the cost goes up exponentially because the expectations that we have are exponentially higher than they were before if we keep doing things the same way. So this is the goal. How do we cope with that increase in demand? This is sort of what we're trying to fix. So again, to sort of step back a little bit before we try and solve the problem, what is an internet application? Like, we've sort of looked at what we consider, the internet, what the internet's becoming. What is an internet application itself? The canonical example obviously is search. My incredibly good drawing again. Search, when I started building stuff, 10, 12 years ago, we would do things like, oh, we need to search something great, we're just going to connect you straight to the database. And like, we have so few users, you can just query our site live and we'll just make an SQL query for each user, right? And back in sort of 98, nobody really thought that was crazy. Maybe you did a bit of indexing in the database and everything was cool, right? And that seemed like a scalable solution at the time. Now, imagine if we did that with web search. You sort of have the browser, it goes to the server then crawls the entire internet, brings it back, and then goes, here's your result, right? That would take absolutely ages. It would just, it wouldn't work. And actually, I know from working at Yahoo, computing the search index, so like Yahoo going out and spidering all the sites and then indexing all the search terms took about a month with like 2,000 computers, right? So 2,000 computers to do the compute, more computers to like, go out and do the spidering, right? So it's a really significant amount of effort in order to do that. So that's not a feasible solution, right? Nobody would use the internet if you typed in like, restaurant downtown Kuala Lumpur, and then you got a result a month later. Nobody would use that, right? It's ridiculous. So we do something else, and this is how all internet applications look like to some extent. We take all of that computation that we have to do, we shove it in a corner, and we do it offline. We do it away from the user, and then we stuff the results into a database, and we end up with this simple flow where the user says, I want to use the application in this way. Maybe it's search, maybe it's getting the list of the money in my bank account, whatever it is. The end user they use the application, and we end up with this routing problem. So the front-end server basically says, the user wants this kind of data. They pass that off to some web services, database, whatever, which goes and retrieves the data from wherever it currently is. Maybe there's a small amount of processing. They bring it back, the front-end server then renders the data, and we shove it back to the user. But what we try and do is we try and move all the actual computation as far away from the user as possible, right? We try and remove as much of this as possible. And this is, if you look at, things like Facebook, this is their biggest problem, is they're trying to find desperately as many ways as they can to make it so that when you use Facebook, they don't have to compute the page that you see. Now, inevitably, because of the nature of Facebook, they have to use some computation, but they have all kinds of tricks. So, for example, and I was talking with Evan Weaver after the Performance Unleashed conference. Some of the things that they do, they take photographs that nobody's seen in a while, they bury them off on some file server over there, and it suddenly takes, instead of 100 milliseconds to look at the photograph, it takes a second, right? Because they pushed it off to some secondary system. But that's okay, because it's a photograph that nobody's seen in a while, and users will deal with it a second. But it's all of these ways of like pushing the things that users do most to the surface, so that the computation isn't the most significant factor. So we can compare this with sort of traditional approach. Now, I don't know, did anybody ever use punch cards? I never used punch cards. Oh yeah, we talked about this before, didn't we?
Yeah.
so my colleague,
Started already in 76.
76.
Wow. So Fortran interaction.
Yeah. So you use punch cards on Fortran, or Fortran on punch cards.
Yeah.
And basically, this is the model, right? It's like, you put all of the data on the punch cards, then you feed them into the machine, and the machine processes for like a day or a week or whatever it is, depending on the data, and then it spits out a report, right? And the big volume of that is the computation. Like we have to do like this much computation, and that's the blocking factor, right? So basically, what we built was we built these, and think of like the early, the original applications computers, crack the Nazi code, right? Feed in a bunch of data. It's just a single program, and this is like the heritage of all the computers that we do today. Is you have a single program you run through it. When we got multi-user computing, nobody wanted to rewrite all the programs. So what did we do? We invented threading, right? We invented a model where everybody could pretend that their program only ran, in a straight line, and then we built into the operating system something that basically just lied and then split the CPU between both programs, right? Threads are just literally like CPUs can't run multiple instructions at the same time. They can't run multiple instructions at the same time. They do them one at a time. That's their logic gates. That's how they work. And threading is just an abstraction. It's not an abstraction that you as the programmer have to deal with, but it still exists. The difference is that now we've moved into this kind of communication-oriented age. We have a completely different model of the critical path of the application. It's no longer like, feeding in the data and then sitting around for a long time for computation. We took all the computation-intensive bits and we shoved them off into a corner so that when we're doing these user applications, they're really fast. So the computation bit, the batch computing still exists, but it's the database computing the index when it has downtime. It's the Hadoop cluster, processing the inbox, the index of the inbox. It's like all of those things, right? And we push them off into a corner so that when the user accesses the application, they get a flow that looks like this. So you've got the client to the server, so the browser accessing the front-end web server. And typically, if that's like a landline connection, if you've got a fast connection, maybe it's 20, 30 milliseconds if you're lucky. Could be 100 milliseconds. If you're on a mobile connection, it could be 3 or 20 seconds, right? I mean, it's a huge gap. And then you have some computation, some like rendering and stuff. And then you have going to the database, fetching the data from the database. And again, it's like the database has caching. The actual going to the database takes longer than it takes the database to go, oh, this is in my cache, here you go. Right? So all of these things, the actual piece of the computation, the rendering the page, the stuffing some JSON data into markup, is actually really small. And probably we've been using programming languages and programming styles that have been optimized to this previous sort of model of computing where everything is batch-oriented. So we want to get away from that. So the traditional approach is basically, I'm translating the traditional approach into how we build web services like this. So you start off with a server. So if you're using PHP, this is like Apache with mod PHP. If you're using, Java, it's like Tomcat or JBoss or whatever, right? You start off, you take some of the resources of the server, and you allocate them to running a web server. Every time you get a request, you create a slice of that server, and you say, this belongs to this user. So we've created a runtime so that we can treat this user as a top-to-bottom program. So we create a space on the server for this specific user. So we can treat them like that batch processing. We start at the top of the code, we run to the bottom of the code. It's easy to think about, and it just runs from the top to the bottom. The problem is that we've now given that user a fixed slice of the computational resource of that machine. And typically the most expensive resource that we have available is RAM. And as you get more users, you slice up, and obviously, my incredibly scientific pie charts, but you get the idea, right? You slice up the machine, and it's these fixed slices, so the more users, until at some point, at some predictable point, you can say the machine is full. And obviously that depends on the size of the virtual machine, like whether it's a JVM, whatever the JVM heap size is for like a specific user thread. But this is like a fairly predictable amount. The event-driven approach, and this isn't unique to Node, but Node is something that's really popular taking this approach. The event-driven approach basically says, we start off, we allocate something to the server itself, and then for every connection, we create a placeholder. So instead of giving it like a big fixed amount of resource, it's just like writing a note saying, at some point in the future, we're going to get some I/O, right? At some point in the future, this client is going to give me a piece of data in order to do something with. So if you're talking about HTTP, it's like, I'm going to get their web browser is going to send me some request, or if you're talking to a database, the database is going to send me some data back. But each one of these, we give it a tiny placeholder, and we don't do anything with it until we actually get it. So we end up with these tiny, tiny placeholders, but they're really thin and light. And then when we actually get some work, so when we actually get some data, we can give that a much bigger piece of memory, and we can say, now you can process that, now you can work through that, and what we're going to do is we're just going to take the data that is now immediately available, and we're going to process it. So this is a distinct difference, and the thing that's important here is because we're using the resources of the server much better, we achieve two things. The first thing is we can achieve much lower latencies because the server is it's the least utilized as possible, and we have this very predictable growth. The second thing is that we can fit many, many, many more times of users on the machine than the traditional approach, because we're not pre-allocating all of the resource to that entire critical path.
You done?
Yes. Yeah, of course. Go ahead.
With this, have you done any benchmarking and stuff in relation to AWS and how that compares to, say, AWSUGMY?
AWS?
Oh,
like DDoSing the...
Yeah.
I've done, well, yeah, I've actually done tests that kind of like folded everything and put it in. So I don't have it on the slide deck, but I was working with a US carrier, so like a big telco, and they basically they lent us the equipment that they used to test the transatlantic flights. We destroyed some servers. And I mean, again, it depends on the kinds of tests you do, but the throughput's really high. I mean, typically a really good way to actually destruct test the stuff is to use loopback, because loopback is often faster than it's possible to get through a network card anyway. So I think it's many gigs of throughput per process on loopback. So I mean, I've got some more specific benchmarks at the back, but yes, I mean, like compared to a traditional back, the response times are really good. And actually, if you just go on search on Google, there's actually lots of people that are like doing publishing these results. I'm working on some more benchmarks that I have to finish for OSCON in 2 weeks, so I'll probably publish those then. And a lot of the work that I'm doing right now is we're doing all this work with carriers, and one of the things that they're really interested in is the idea of consistently connecting stuff. So this is a complete slide to the talk, by the way. But basically, so you can imagine like the billboards, right, or your cell phone, like those things are connected to the internet all the time. And if you allocate like a big wad of memory to every device that's connected, you soon run out of memory. Whereas if you give a really small amount of memory to each device that's connected, and then only give them more memory when they're actually active, you can fit many, many more devices per server. So we were looking at something in the range of 20,000 on a Dell 510 with Java versus 700,000 with Node. Now, we wouldn't really deploy 700,000. That's unrealistic because when you did get workload, you wouldn't be able to service that entire workload with that server. So we'd probably cut it down to like 300,000. But 300,000 versus 20,000 is still a bloody difference. So that's the kind of stuff that we're aiming at. So let me do like the short intro to Node. It's a really low thing, so I'm going to probably rely on my slides a little bit. I'll do some live coding again, but I'll start by relying on my slides. So Node is server-side JavaScript. So it's basically, if you think of JavaScript in the browser, in general, like, lots of people have strong opinions about JavaScript. The strongest opinion that most people have after programming in the browser is they've decided they really hate the DOM. Which is, and they particularly hate the way that the browser's inconsistently implement the DOM, which is also fair enough. So this is not a problem that we have because we run pure JavaScript, obviously. We took the Chrome engine outside of V8, or the V8 engine out of Chrome. So basically, Google built Chrome. And in order to make it the fastest browser, they did all kinds of like interesting things. And one of them was they hired the team that wrote the current Java virtual machine called Hotspot. And they basically hired that team, and those guys are now building what is the JavaScript runtime in Chrome. So we're able to leverage that work. I have strong suspicions. Basically, the things that Lars wanted to do with Hotspot, or like the different approaches that he wanted to take, he's putting those into Node. Now he's not working on Hotspot. So I'm kind of, it's definitely, a younger VM than Hotspot, but I'm pretty confident with it. And then it's non-blocking IO. I'm going to explain this more in a minute, but essentially what that means is that whenever you do input-output, so we saw how the input-output, both to the network and to the database, but also to like hard disk, that's one of the slowest pieces. So whenever you do I/O with Node, it's non-blocking. It doesn't. It's all asynchronous. None of it is inline in the code. And I'll talk about that some more. And one of the goals that we had is like, we all came from different backgrounds, but like nobody wanted to be like less fun than Ruby or less fun than Rails or less fun than, it's kind of, we weren't going to set out to build something that oh, I want to build stuff. But it's going to be really fast, but gosh, it's going to be really annoying. Nobody would do that. So one of the important things for me as a developer is that it's easy to extend. We have a great module system, and it means we've got tons of external developers. I mean, I was talking to somebody earlier. We have over 25,000 community contributed modules in the first 2 years. you know, so that's, you know, and not all of them are good, obviously, because it's open source, but, you know, all of them have some of this special baby, even though that's terrible. I've been doing open source for 10 years. I'm allowed to say things like that now. You know, but this is, you know, it's actually, for me, it's been really exciting because, you know, I feel like I'm running a rocket ship. I honestly, in the, you know, in the 10 or 12 years that I've been doing development, I've never been on a community that's this active, you know, and it's kind of, you know, in some ways, I feel good because lots of people are taking pot shots up at us right now, you know, like, my framework is about the node, or this is about the node, or node's stupid, and I feel that's because we're doing something right and people feel threatened. So this is a node shell. You can just type any console node. If you have Windows right now, sorry, the experience isn't great. We have a partnership with Microsoft.
How long?
5 months or so. You can do it right now. There are actually really good install instructions. You can install it using something called min-GW, which is basically GNU tools on Microsoft. I don't really encourage anyone to do it with SIGWIN. Yeah. So basically, we're currently working on that. You know, the current latest versions of Node. I mean, obviously it's open source. You can see as we're building it. The current latest versions of Node are built on the shared platform for both Microsoft and Unix. And you can download those and install them within GW, and all the instructions in the wiki. But yeah, if you start Node, we can do like all your typical JavaScript stuff. I quite like this. If you've never seen JavaScript WTF, yes, WTF, you should go and look that up. It's pretty funny. It's one of those sort of idiosyncratic things about JavaScript that's so awesome. Like 3 is better than 2 is better than 1 is false. Watch out for yourself. So you can just type JavaScript. This obviously is not how you run a program. It's just a shell. You know, so if you use like Python or if you use Ruby, same thing. You know, you can do console.log like as if you're in Firebug, so that kind of thing has come over. You know, you can clear the context. So here's an example. If I set a variable called foo, set it to var, and then I clear the context, if I then try and access that variable, it gives me a stack trace. And this is actually one of the nice things, you know, in the server-side implementation, is the stack traces are actually really good stack traces. And more than, have I got pointer? Yeah, there you go. Then we got cat. You can see, so the first exception is object context 1.1, which is basically like line 1, because we're in the REPL shell, right? But then you can also see like REPL here, events, readline. All of these are JavaScript. All of these files, REPL, events, readline, REPL, like all of those files are written in JavaScript. Node itself is written in C in some places, but a significant amount of code is written in JavaScript. And this is actually kind of nice. Hands up again for the do PHP. Right? Hands up. Keep your hands up. People that do PHP, keep your hand up if you've actually read through this, the PHP source code and understood it. We have no hands left. And this is not to say that like PHP is bad or wrong, but one of the things that I personally enjoy about Node is the fact that, you know, and I'm actually learning C++ again, you know, because I want to sort of get really, really in the heart of it because of, you know, my job. But one of the things I really like about Node is I can dig into the guts of it, right? We have a package manager called NPM, Node Package Manager, all written 100% JavaScript. You can go and read it. You can see what, you know, when you know you want to contribute back to the community. There's no like magic voodoo. You know, I mean, if you've ever tried to look in like Rails core, it's awful. You know, you need a hug afterwards because the HH has got a twisted mind. In a good way. I mean, the guy's bloody smart, but you know, you know, for me, this is an important thing. It's turtles all the way down, and I really like that. So what I'm going to do next is I'm going to step through the website. So this is the kind of example. Has anybody run this? I think a couple of people have run it. So this is like a canonical Node example. This is not typically how anybody writes applications, because this is really low level. So in Node, you know, we don't have an Apache, we don't have a Tomcat. Node itself is the server. Node acts as the server. if you put Apache in front of Node, you're just going to get, Apache speed performances. So no point doing that, right? This while it's sort of the canonical learning example, it's good to understand how it works. When people typically build applications for real, they'll use a framework like Express. So has anybody used Sinatra for Ruby? A couple people. It's like that. It's an MVC framework. So when you actually build applications for real, you wouldn't do something at this low level. You'd use an MVC framework to do most of the work for you. But the MVC framework itself would be leveraging this code. So yeah, okay, good. So like, this is like the top 6 lines of web server. It's not a very good web server, but that's okay. So the first thing we do is var HTTP, create an HTTP variable, and inside it we put the HTTP module. So require is the way we include modules. You can define your own modules. There's nothing special about these. There's a path structure. So like think like the class path in Java, right? There's some places where the different libraries live. You can also put paths inside the brackets in order to refer to things in the context of the file that you're in. So this just includes the HTTP library. So we now have a variable called HTTP that includes that library. The next thing that we do is we call create server. So if you're used to object-oriented programming, create server is just a factory method. It just creates a new server object. You could also do HTTP, or you could also do like server equals new HTTP.server, and it would create a new server. And inside this, we pass a function. Now, this is one of the things that you may not be familiar with if you use other languages. JavaScript has first pass functions, and what that means is that you can pass a function as an argument to another function. So you can pass functions around as if they're variables. And in this case, we just define the function in line for sort of convenience sake. But this function is going to get called when something happens. So typically, with the different kinds of servers, they'll have some important event which will get called whenever you sort of pass a function to the factory method. And then we use containers to basically say, I create my server and I want it to listen on port 8124 on localhost. And then we elaborate the function that gets called. And what actually happens is it's a request. So when a request gets called to the web server, so when somebody points their browser at this web server and runs it, this is the function that gets called. So what we do is we get a request object and a response object. We take the response object, we write an HTTP header, which is this, and then we write a response back. And the end method it writes the response and then it closes the connection. So it's pretty simple, and then we simply we console log that. So actually what I'm going to do, I'm just going to you guys can see. Can you guys see that okay? I'm just sorry on the right side. So I just entered like a node shell. I'm just going to do it like in the shell because I've done this quite a lot. So I'm just going to require the HTTP library. I started coding without semicolons. It's quite liberating. You can do it too if you like. So I'm going to do it in a slightly different style for an example, so you can sort of see some of the alternative styles. So I can do something like this. The shell also has, should be new. The shell also has completion, so if I do like that, right? Ooh, wait. Why you guys are impressed by easy things? If you like, I've got some great watches. See me around the back. Genuine Rolex. So I've got my server, right? I've created my server. And what I'm going to do next is I'm going to do on. So this is a common theme of the way that we code. So basically everything being event-driven, we use this on method. So this is how we convey the fact that we want to listen to an event. So we do on request, and then we create a function, different type, request response, right? So we now have an event listener for the request event that happens on the server, and it's going to call a function. So I'm going to do, write head 200 because I'm lazy. I'm not going to catch any of the things. It's okay. and then I can do, write, hi, my LSS, and then res.end. And then I close the curly brace to close the function. I close the bracket to close the function call. And then it returns me the server back. So okay, so what I can do now is I can do server.listen, and I'm going to do like 8,000 or something. Because it didn't pass an object, it basically binds on all the IP addresses on the machine. So I can do that. Okay, so good. Now I can open the browser. I can do this happen to have this one pointed as well. So you can see it's basically it's just done like that. It's not, and it didn't put any spaces in it, so it's a bit run together. It's not very impressive. I can probably get that and, I don't know, double tentacle. Sadly, I can't do too many on that. Okay, so I've set my folder script limit to 10,000, so basically I'm going to try and connect like 10,000 connections to this at the same time. 10,000, and then, so this is Apache Bench. It just load tests stuff. 1.1. Right, so this is running on my MacBook Air, right? And obviously that's like the world's crappiest web server. It only does one thing. But even running on like my MacBook Air, which is not exactly the world's biggest laptop, I have it because it's convenient to fit in my bag at airports. We can just like flash through stuff. So this is the goal, is to have like a really fast response time. You can obviously, and this is not a hard example, but basically everything except like a couple of requests were a millisecond or less, and then one request was a teeny bit slower. So this is the kind of thing that we really want to have. This is the kind of experience that we want to have, where we can basically easily code something up that's really fast. So why is this suited to internet hacks? So this is kind of a fundamental part of JavaScript, is the event loop. So if you've done JavaScript programming in the browser, you've used the event loop. The thing that's different is the server really forces us to use it sort of much more, like in your face. And this is a deliberate design choice. I mean, like often, like people ask, like, oh, are you going to support threads? And no, never. And people have extended it to do that, but it's never really caught on. And the reason is that by picking this paradigm, we get a really simple experience that allows you to write these really sort of fast, high-performance servers. So what is the event loop? The way that I think about it, I'm vegetarian, so I cook a lot. And, I love cooking. But, imagine if I'm sort of chopping some vegetables or something, right? And a pan starts boiling over. What I don't do is keep chopping and then try and turn the pan off. I'm either going to scold myself or like lose a finger, right? That's, it's not, humans aren't built like that. Humans can't really multitask. Humans can't actually do several things at once. In the same way that computers can't do several things at once. Humans are really good at something else though. Humans are really good at splitting their attention. So what I can do is I can be like, oh, well, I'm chopping. Now I'm going to put down the knife, turn it off, and carry on chopping, right? And I don't get worse at the chopping because I turned off the stove. So humans are really good at switching their attention very fast. And I think this is the style of programming that we're doing. Is basically what we're asking is, we're not trying to create a place where the server is doing many things at the same time. We're building a server that's context switching very fast. And underlying everything, the computer's already doing this anyway, right? If you're using threads, the computer's already just context switching, but the operating system is doing it on your behalf. In this model, we push that, that small amount of complexity up to you, the programmer, but it allows you to manage the resources of the server much more effectively and get a much better response time. So, I think of this as multitasking one thing at a time. I have more bad analogies, don't worry. The other one I like to think of is invented postman. Even though I live in America, I insist on calling a postman. Partly more because it winds up the Americans than they actually care, but, so the mailman, obviously, all men are male. The postman basically, the postman has like a stack of letters to deliver, right? But he's only got one set of legs. So if he wants to deliver a letter, he has to walk down the route to the house. He can't physically walk down 2 routes at the same time because he's only got one set of legs. So he takes the first letter, think of it as an event. So I get a request from a web server, and I pick that up, and I walk down the route to deliver that to the house. Think of the route as the function call. So like, here's my piece of code that I'm executing. So I walk all the way down this piece of code to the end, and now I've walked down that piece of code, I can go back and I can deliver another letter, another request, and walk down another piece of code. But because I've only got one set of legs, I can't walk down 2 of them at the same time. It's just not possible. But what I can do is I can just kind of do this one, then I do the next one, then I do the next one. And this is how this all works. So if we take that sort of example that we did, when we walk through it, we can sort of see how it works. So the first thing that happens is when we run this program, Node reads the whole thing from top to bottom. I call that sort of main, like the evaluation step. And what we end up with, so we sort of process this whole thing, and we say, right, we've got some variables. We've got the HTTP variable contains the module with all the HTTP library in it. We've got a server variable, which contains the HTTP server, right? And then, because we did server.on request, we've got this event listener. So we created an event listener, which is the server.request event listener, and it's got functions next to it. The next step is that we run the event listener, right? So the event listener is basically, do we have any active listeners? Check, do we have anything waiting that's expecting an event to happen? If we don't have anything, then Node will just exit, right? If there's nothing to do, Node will just be like, I'm done. But if we do have some function that's sitting there waiting to go, oh, an event happened, I need to respond to this, then we sit down and we wait for that event to happen. So we created one server.on request, so we have that waiting. So the server will just sit there and wait forever until it gets a request. At the point that it gets a request, we then do the event call. So step 3 is the event call. Now, the thing that's important to realize is, obviously, like this is 3 lines of code, right? If this were 100 lines of code, if it were 1,000, if it were 1,000,000 lines of code, right? And we got another request in while we were executing those 1,000,000 lines of code, we wouldn't stop processing the next request. We would add that to the queue, and it would be processed after this request. So step 3 is we sort of, we get a request in, and we deal with the request. So we go through that piece of code, but while this piece of code is executing, specific to that event request, we're not going to execute any other code. So all the code is being executed in serial. But what we're doing is we're able to accept new events. So I got a new request, I got a new request, I got a new request, and all those requests are stacking up while this code is running. Now typically, because we saw on the big sort of on the flow chart, the actual amount of work here is tiny, tiny, tiny. So what happens is you're just doing requests like this. So like you get a new request in, and you're practically dealing with you're dealing with many seconds, right? These things are happening in microseconds. So you're just dealing with them as they're coming up. And that means that you can service things. Now the other thing that's really interesting is, you get a request in from the browser, and it hits the server, and the first thing the server does, it goes, great, I got this request in from the browser, now I need you to go over and get this thing from the database. And then it stops doing anything with that request. It sits there, and it waits for the database to come back, and then it starts doing it again, right? So while it's waiting for the database, we can pick up a different request and service that one. So it's all about this kind of, juggling, right? We're just juggling the requests. And once you've dealt with a specific request, you just go back to step 2. I'm waiting for a request again. If I have one waiting, I deal with that straight away. If I don't have any waiting, I just wait for one to come and happen. And this is where the non-blocking stuff matters. So, the event versus thread gets really important here. So this is like a Node.js style, and this isn't real code. This is sort of This is like code to make the example really easy, but you can imagine like query mysql.query equals select something from a database, and then query that on result, you do something, right? So this is, it's really super vague, but it's to illustrate the point. So this looks a lot like what we just did, right? This is more like you doing PHP or Java, right? This is, result equals mysql.query, and then I get my result, and then I process through the rows of my result, right? This is more like the traditional model. Let's look at these two things together and actually see what's happening. So if I do this for x times a string, right, what happens is we're just assigning something in RAM, right? We're just assigning a string, I'm string, in memory, somewhere in the computer. So it takes about a nanosecond, or probably like a fraction of a nanosecond. Like CPUs are like, what, 3 gigahertz or something, right? So it takes like a third of a nanosecond in order to run an instruction in a CPU. It takes 2 nanoseconds to get from L1 cache in the CPU, 5 nanoseconds to get from L2 cache, and I realize this is deeply nerdy of me, so bear with me. It takes 80 nanoseconds to get stuff from RAM, right? So to get stuff in and out of memory takes this long. So this operation, all of the things inside this operation happen within this sort of scope of speed, right? So everything's happening, like the slowest parts of this are operations. This is like this assignment is probably, like 4 or 5 of these operations together, but none of them are slower than 80 nanoseconds, right? This, like the server making a query and then getting a result, is going over a network, right? It's going over some slow piece of infrastructure. You can even imagine this is like a hard drive, right? Even doing a hard drive, getting stuff off a hard drive is a lot slower than getting stuff off the memory. So let's evaluate this. So if I do it in the traditional style, and I do something like this, result equals mysql.query, the time it takes, these aren't nanoseconds, these are milliseconds, right? So it takes approximately 100 milliseconds to run the query database, maybe. It depends how thorough the query is. So you can adjust these figures up and down. 50 milliseconds round trip, right? So what does this mean? Well, let's compare it. If the local variable is cat, I can say, I love being in front of an audience because you all have to do what I say. So if the local variable is cat, right? The remote operation, can everybody imagine a blue whale? Right, great. The local operation is 100 blue whales compared to the cat, just like that. I mean, that doesn't even come out on the screen. So this is the point, is, when we use this style, where we basically say, I'm going to do a variable assignment of some result from a database, right? That operation, is like the difference, and depending on how fast the database query is, or how fast the network is, you can don't call the blue whales. You can set the blue whales free or something, but you can have less blue whales, and the difference is still really significant. I think for me, I'm kind of a visual person, as you can tell, but like trying to imagine that difference is like if you basically have a programming style that says, I assign to a variable the result of this really intensely slow operation, and my server relies on the fact that I'm able to like flip out these operations really quickly so that I can deal with the natural class. Obviously, these two things do not go together well. And this is the reason why everything is an event callback. Everything that is I/O, everything that is slow, we use as a callback. So, when this slow event happens, then run the code that deals with it. But the other thing that's important with this is if you have a thread, right, and the blue, you have to do like a blue whale operation, for the entire duration of that operation, you're assigning the full amount of memory that you need to do the entire user request all the way through. You're assigning that for the entire span of the blue whales, whereas Node is doing it for like the span of a cat. That sounds, I don't know, that's mind-bendingly awkward, but it's a metaphor. So in this context, blocking is a better topic. If we have operations that are so slow, we might as well stop the server. Like, we can't handle any new requests because we're dealing with this massive thing, so we don't do that. But threading also wastes memory because of the programming style. So we don't want to do that either. So here's an example, right? If you take a PHP server and it's like 2 megs per user, maybe you guys know how big your VMs are, I don't know. Like, you know, 2 megs is not completely unseemly for a PHP server with a bunch of stuff installed, right? So if you've got 2 megs per user and you've got 8 gigs of RAM, right, you can do some really back-of-the-napkin math, 4,000 people, right? 4,000 connections. You know, and again, this is not like a benchmark. This is just, you know, mean and napkin. Node, each HTTP connection, including the TCP connection, is 6 kilobytes, right? Now we still have to do some like work over here, right? But just like again, like really back-of-the-napkin math. So we start off, we divide 8,000 by 0.006, and you get 1.3 million. You then divide that in half because you need a connection to the client, and you need a connection to the database. You know, so you still need 2 connections. But you know, still 650,000. And then if you like tune that down and say, well, you know, realistically, we're not going to get 650,000. Let's be really just mean and like, you know, I don't know, do like a quarter of that. You're still kicking the pants off the traditional approach. So this is the point. This is not magic. There's no like Node isn't fast because you know Ryan Dahl you know went to Germany and became enlightened. You know, well maybe he became enlightened, but you know, and he go to Germany. That is certainly true. But you know this works because this is a good architecture for building servers that do internet stuff. It's a good architecture for building servers that do communication stuff. And an example of this is, you know, the benchmarks that I like, in order to like simplify the comparisons, Nginx is an event-driven file server, right? It's really bloody fast. Apache is a threaded file server, you know, and obviously if you sort of attach like every possible Apache mod, it's going to be really slow. But if you know, even if you just run it bare bones, as you add more and more users, and as you add more and more connections, Apache just tanks. Because what's happening is Apache has allocated like all of its slices of memory to a user, and it has to finish that user's connection before it can free up that slice of memory and give it to the next user. Because Nginx is using the memory much more efficiently, and you can see like the specific blog post there, web faction, where he has like all the specific stats and stuff. Because Nginx is using the memory much more efficiently, even as you like pile more and more concurrent users on, it's still able to service a really high amount of connections. It doesn't affect it because it's not actually spending its resource at holding on to those things. And then you have a similar story in terms of like the memory footprint, where Apache is just like, poof, it just shoots up. So I'm gonna do, how much time do I have actually? I'm gonna do like a bit more coding demo in a minute, but you know, basically the point here, like the summary, like out of all of this, is Node is designed to do communication. I mean, this is the simple fact. Node is designed for the kind of internet applications that we build, and this is why it's better. This is why it's faster, because it's designed to fit the purpose of the kind of applications that we build. How much time do we have?